So, a very good morning to you all. And atom, molecules. So it is going from very smaller level to higher level, and then it goes to human being. And then we, as a human being, we always interact with certain environments. So we always interact with our environment, say plants. Sorry. So always interact we always interact with the environment, say our troposphere, our biosphere, and then uh, ultimately to our earth. So we always exchange sorry I'm so we always exchange energy with respect to our surroundings, and then this environment or ultimately to the earth, and then our earth, it is connected with the solar system. So it continuously interacts with the planets and sun. And sun is a star which also interacts with the different stars, our Milky Way, and then our Milky Way is a part of universe. So in the philosophical sense, or in context to self awareness, in context to self development, it is said that we human being is not only just a body, but when we are alive, we are continuously interacting with the infinite energy. That is, we are connected to this universe, so we have lot of potential, and then this gives lot of motivation to people to uncover their potential. It gives strength to the people. So though we say that, okay, when we talk of biomedical signal processing, that we stop till human organisms comes, but beyond that there is a philosophical and spiritual, and which is also correct. Okay, so I am not going or diverting myself to the topic, but now again I'm coming back. So we saw the levels of structural organization, which starts from atom, and it's different levels it goes to organism. And now it's also important to know about different planes of a organism. So here we find three reference directions, because sometimes, like, as our human organism, or even if we consider some organ, say if we consider a brain, or lungs, or heart. So these all are 3D objects. These are the three-dimensional objects. That's why it's very important to get the reference of those things. So, like, unlike for other signals where we have x, y, and z axis, here we have also different planes, and these in the medical terms we have some reference direction. So if we can see here on this slide, so we cut uh, if we cut just suppose if a person is standing, and if we cut just half of it from the base, then it is known as transverse plane. Okay, transverse plane. So it is in the x-axis. We can see x-axis, transverse plane. So it will cut body into two parts. And then there is another way also to get the slice of the organ, or the body, or just to show the reference. So if it takes half from the y-axis, then it becomes sagittal plane. And then if it takes the front and back part, and it goes through one plane in such a way that it gets the two parts, which is shown here. So that is called coronal plane. Okay, so we have three reference direction. One is transverse, which is say when a person is standing, it will be parallel to the head, and it will be parallel to the foot. Okay, so this will be the parallel line. Again, if it's a sagittarial plane, so it will pass through the mid of head to that of it will go to the last portion where we have a pit in between the two pits. And then we have the coronal plane. Coronal plane will pass in such a way that that frontal part and the back and the postural part will be separated. So we have three different directions. So these are very important in order to study different kinds of organ, like a brain or lungs organ. That's why so these are the medical terms, like we have a transverse plane, or we have a sagittal plane, or we have a coronal plane. So with this help, with this knowledge, we can classify this. So this first one, if we see this first one, so it's a transverse section. So here the brain is divided into transverse sections. So we can see the previous slide here. So it's a transverse section. This one is the transverse. So here if we see, then this is your this is the transverse section. Similarly, we have when it goes from the top to bottom, so we can relate this when it goes to top to the bottom, so it is sagittal plane. So this one is the sagittal, this one is the sagittal, and this last one is this one coronal plane. So we can get the different reference direction to study different part of a brain. I hope these are clear to everyone. Okay, so there are certain definitions, like in the medical terms, like we have certain definitions. So when we talk of, say, superior, so superior basically it's towards the head or towards the top. So these are the superior. So in medical terms, people may say that, okay, we have to take the recordings from the superior. So means it's the towards the top or the towards the head. So the area which is towards it, these are known as superior. Likewise, we have, say, inferior. Inferior. So we can see here inferior. So it's away from the head. So it moves towards the bottom. Then we have a anterior. Anterior means towards the front. Okay, towards the front. Likewise, we have different medical terms, so we are not going much in detail. Just we should know these things. Like if we say uh, anterior, then we can say that, okay, this is the anterior part of the brain. So it's the frontal lobe, or it's the frontal part. So now, as so it was just about different levels of levels or the different structures of organization, and then we saw like there are different reference sections available for knowing or for studying the different organs or organism. And then we know that it's so whenever we deal with the biomedical signal in biomedical signal processing. But before that, as we previously also discussed, that basically when we talk of a signal, so signal is a physical quantity that varies with respect to certain independent parameters. And basically system is a hardware or a software or a combination of both, which operates on the signal to give a desired output. And signal processing, it refers to extraction of information from the signal. So it means that this signal processing, basically it refers to study of signals, systems, and processing. And signal have different types. We have different types of signals. Signals have different nature. Their analysis techniques will be different. We will have the different components of a signal. Then systems, there are some system properties, like it is causal, stable, and there how to get the response of the system. Okay, so these all comes under signal processing. So we will see those things also. But when we say processing, so basically it's a method for analysis and processing of signals and systems. So this processing, basically it applies certain signal processing techniques and algorithms in order to extract information from the signal. There are lots of scope for the signal processing. And when we do signal processing, we search for some feature from the signal, so that some pattern recognition or some data information can be obtained from the signal, which can be finally used when application of machine learning and deep learning will be met. So now we are moving towards biomedical signal processing. So as we know that that signal is any physical quantity. Why it's a physical quantity? Because we can measure certain parameters of the signal, like maybe its amplitude or frequency. So so basically this signals refers to any physical quantity that varies as a function of an independent variable. Independent variable is usually time, but it may be space, distance, or any parameter. And biomedical signal, now we are coming to our main uh, field, that biomedical signal. So biomedical signal, basically it's a signal being obtained from a biologic system or originating from a physiologic process. So it may be from human or animal, and then it helps in for the medical care of the patients. So biomedical signals are those signals which are obtained from some biologic system or which originates from the physiological process. So this physiological process may be like from the beating of heart, some if some signals are coming, for example, so that will be like electrocardiogram signal. So electrocardiogram signal or electroencephalogram signal, that is brain waves, phonocardiogram signals, speech signal, these all are termed or can be considered as a biomedical signal because it originates from some biological system, or it originates from a physiological process. And the processing of these biomedical signals is done for the treatment. So all treatment of biomedical signals which occur between their origin in a physiological process and their interpretation by their observer, uh, that is to the clinician. So basically this process of biomedical signal refers to, so why we do processing, or why this what we mean by the processing of biomedical signals. So at first we cleared our concept about biomedical signals, that biomedical signals are those signals which are obtained from some biological system or which originates from a physiologic process. For example, electrocardiogram signal, so which is basically a recording, it's a recording of electrical activity of heart. Similarly, if we say brain waves or electroencephalogram signal, so basically it's a recording of brain activities. Okay, if we say phonocardiogram signal, so it's a recording of sounds produced by the beating of hearts, or the sounds produced because of the flow of blood and closing and opening of ventricles and arterioles. So so that's why we have so that's why these electrocardiogram signals, electroencephalogram, these all are biomedical signals or bio origin signals. And this processing of biomedicals includes, or rather it tells that all the treatment of biomedical signals, all the processing of biomedical signal which occurs between their origin in a physiological process to the at the end to the interpretation by their observer, clinical, that is to the clinician, to the medical expert. So so this processing of biomedical signals, it comprises, or it uh, starts with the origin of the signal, from where it has been originated, from that point, means from recording, then it's processing and then giving the output to the observer. So everything comes under the processing of biomedical signals. So when we see the generalized block diagram of a biomedical signals, like processing of biomedical signals, so this slide basically tells about the processing of biomedical signals, that how what is the typical steps involved in processing of biomedical signal. So we can see that here, this is a say, this is this a subject, or it's a say human body, from where we would like to acquire some of the signals. Say someone would like to acquire electrocardiogram signal, or say brain waves or speech signal, whatever we are interested in. So here it will be, so here it will be a biomedical signal. So as we just discussed, that these biomedical signals are those signals which originates from some physiological processes, or which originates from some biological processes. So definitely, if it originates from some of the physiological process, say we are interested to know the body temperature. So 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 these biomedical signals will be in the form of some physical parameter. Say it will be, say, blood pressure, or it will be body temperature, or it may be heart sounds, or it may be heart lung sounds. Okay, when someone puts stethoscope on the right area or the right part of the chest, then a doctor with the help of stethoscope can hear those sounds. Okay, but these all biomedical signals are basically, these are the physiological variables. Okay, that's why we need a transducer which can convert these physiological signals, or biomedical signals into its corresponding electrical signals. Okay, that's why here we have a transducer. Now if we would like to measure a body temperature, then here we must have a temperature sensor as a transducer. If we would like to measure the blood pressure, say we know that for a normal people, systolic blood pressure and diastolic blood pressure should be around 80 by 120. So in order to display that, in order to process that, first we need a transducer. So that pressure, or that signal, it will be converted to its corresponding electrical signal with the help of transducers. So we use a transducer. Then after that, as we know that uh, this signal, when it gets converted, it may be contaminated with some noise. So that's why we have, or it should not interfere. That's why we prefer isolation pre-amplifiers before amplifying and filtering the signal. Okay, and then as we have to process the signal digitally, because it has lots of advantages, so we convert that analog signal into its uh, corresponding digital dominant signal with the help of A to D converter, analog to digital converter. And then again, filtering is done to remove some artifacts, because when we are dealing with the biomedical signals, so inside there are many organs. So if we are interested in one particular biomedical signal, then other physiological processes and other biomedical signals may interfere. So maybe like movement of hand or muscles, or while recording when we speak or when we move, or internal phenomenon, or in fact the instrument itself may create some artifacts. So it's always advisable that after analog to digital conversion, we must filter to remove the artifacts. And then with the help of signal processing technique, we try to detect the events and components of that biomedical signal. So once that events or components have been detected, so from that detected components which are of our interest, we try to analyze that event, and then we extract some of the features using signal processing technique. And then once the features are extracted, it can be given for machine learning, or it may be used for pattern recognition and classification, and it will give a decision whether it's a normal or abnormal. And then it uh, can be given to the observer, or to the interpreter, or to the medical experts, which will definitely assist about the person from whom the biomedical signal has been recorded. Okay, Okay, so this is the complete steps of a typical biomedical signal processing scheme, and broadly it can be said that processing of biomedical signals contains broadly three steps. First is signal data acquisition. First is the data acquisition. First we have to acquire the biomedical signals. So that how it is done. So with the help of putting, so it may be invasive or non-invasive process. So these biomedical signals are recorded first. It is done with the help of transducer, isolation, preamplifiers, till this conversion. Okay, so this part is basically signal data acquisition. So once the data is acquired, then we do signal processing, where we remove all the undesired signals, and we detect the events and components which should be fed to the signal analysis block. So mainly this processing of biomedical signal broadly consists of three steps: signal data acquisition, signal processing, and signal analysis. I hope this is clear to everyone. Am I audible?
Yes, sir.
Okay, thank you, thank you. So these are the general, typical block diagram of a processing of biomedical signal. And then this processing of biomedical signal, basically it's an application of signal processing methods on biomedical signal. So biomedical signal processing is a special branch of signal processing, where we deal with the processing of biomedical signals, where all possible processing algorithms may be used, which is there in the signal processing. So like filtering, feature extraction, pattern recognition. So almost all possible processing algorithms which are used in signal processing can also be applied in the biomedical signal processing. But again, we have to classify the biomedical signals, and we have to see that which algorithm or which technique should be appropriate for those things. So biomedical signal processing requires understanding the needs, that is biomedical processes and clinical requirements, and selecting and applying suitable method to meet these needs. And so the first step is that, okay, though we have lots of signal processing algorithms, techniques, but prior to applying any signal processing technique, it's important to classify the signal, because once we know the class of signal, then very easily one can apply a suitable algorithm for processing and analysis of that signal. That's why we need to know about biomedical signal classification. So on the basis of, so these biomedical signals can be classified on the basis of the signal characteristics, and also as signal source. So on the basis of signal characteristics means like its statistical parameters, which is also known as technical point of view. So signal characteristics or signal classification based on signal characteristics, that is the technical point of view. So we go for some statistical measurements there. By measuring some of the statistical parameters, we can characterize the signal. Similarly, these biomedical signals can also be classified based on the signal source, from where it has been originated, from where and how the signal is originated and measured. So there are two ways to classify the biomedical signal. One is on the basis of signal characteristics, and another is on the basis of the source of the signal, that how it has been measured and from where it has been originated. And then we will see the application of this biomedical signal processing in various fields like neurophysiology, cardiology, monitoring and diagnosis of patient. And this classification of biomedical signal helps us in selection of the processing method, that which algorithm should be applied to process that. Because if we have different kinds of signal, like suppose if we have a electrocardiogram signal, and at the other hand we have a electroencephalogram signal, so same algorithm may not be appropriate for both. So we have to choose according to the signal characteristics and the source. Okay, so definitely our brain waves, the amplitude will be very low as compared to electrocardiogram signal, where it will be very dominant. That's why it's very important to classify the signal prior to signal processing. Then we know that the signals can be classified as deterministic or stochastic. And then if we have a deterministic, we know that deterministic signals are those signals which can be explicitly or which can be accurately represented with explicit mathematical relation. For example, sine omega t. So it's a very deterministic signal. Its future can be predicted, or its present value, or what was the past value. So everything can be predicted very clearly, very correctly. So that's why these are the deterministic signals. Whereas stochastic signals are those signals which are somewhat random in nature, and it requires some probabilistic approach to represent the signal. It's not very deterministic. Then if we have a deterministic signal, it may be periodic or non-periodic. So again, like if we consider sinusoidal signal, then it's a periodic. Complex signal can also be periodic. Okay, then if we have a non-periodic signal, then this non-periodic signal, again, it can be almost very close to periodic or pseudo-periodic, or it may have a very transient behavior. And the stochastic, when we talk, we have a stationary and non-stationary signals. Stationary signals are mainly ergodic. Some may be non-ergodic also. And non-stationary signals are very special type of signals. And we will find that our heart sound signals or lung sound signals are non-stationary in nature. So we already discussed about this, that deterministic may be accurately described mathematically, using usually predictable, not in case of chaos. Then periodic, which repeats after certain instance of time. Almost periodic means patterns repeat with some unregularity. Like we will see that our heart sounds are not periodic, but it is almost periodic. Transient means signal characteristics which changes with respect to time. So that is the transient behavior of the signal. Stochastic means those signals which are defined by their statistical properties with the help of some probabilistic approach, uh, like cumulative distribution function, say. Then stationary signals are those signals whose statistical properties, say mean, okay, mean of the signal do not change over the time. So if, say, if I consider a speech signal, not speech signal, basically speech is a non-stationary signal. Suppose if we take a small segment of some signal, say for 2 second duration, and we take the mean of that signal, then again after some time, if we take again the another segment from the same signal, if its mean is same, and it becomes same for every part for that duration of time, then we say that okay, the signal is stationary. But suppose if we have a signal of length, say 10 seconds, and we choose 2 seconds, and we see its mean, and again we take the another part of the same signal having same time duration, and its mean is different, then we can say that this signal is non-stationary. So stationary signals are those signals whose statistical properties do not change over the time. So then it will be termed as a stationary. Then ergodic means statistical properties may be computed along time distribution. So like, say, statistical properties like mean, autocorrelation, so these can be computed along with the time distributions. Say if we consider white noise, then autocorrelation will be 0 except for t is 0. And if we take the uh, flat spectrum, which is also known as white noise, no, flat spectrum, if we take flat, means in the frequency domain. So for white noise it will be flat, so at that time it will be 1. Then so we just saw different kinds of signals, that okay, signals can be deterministic, random, stochastic, or it may be almost periodic. So let us see in which category we can put our biomedical signals. So all real biomedical signals or bio originated signals may be considered stochastic. Why stochastic? Because here if we see stochastic, because this is the stochastic. The reason is because we have to follow certain probabilistic approach. It's not like a sinusoid signal. Because if we consider a segment of speech, and if you would like to represent that segment of speech signal, in that case we have to assume many sinusoids of different harmonics, and if it will be added, then it will be a close to our speech signal. That's why it's a stochastic. So most of the biological signals, or even all real bioorigin signals, may be considered stochastic. It's almost deterministic signal. It's not deterministic, but almost deterministic. For example, electrocardiogram signal. Wave shapes are very the wave shapes that almost repeat themselves, and they show same kind of pattern. But like if we see EEG, so it's truly stochastic. Truly stochastic means it's quite random. We have to use the statistical characterization only. Okay. So that was based on the property, that how the signals are classified. So another classification of biomedical signal is based on source. Okay, based on the source. So previously we saw how the biomedical signals are classified based on the statistical values, based on the technical point of view. But now we are now discussing the classification of biomedical signal based on the source. So biomedical signals differ from other signals only in terms of the application signals that are used in the biomedical field. So we have lots of different kinds of biomedical signals based on the source classification. So one is a bioelectric signals. So bioelectric signals, it is generated by nerve cells and muscle cells, because we know that, as we have seen that our the smallest it starts when we saw the structure of organization. Then we saw there was atom. Okay, atom, molecules, cells. So generally what happens that when we when we are very tired, okay, when we are very tired, in that case, like it may happen that the potassium, or there may have occurred, say, like nerve cells, or the muscle cells have lost the or it has shown some depolarization. But again, when we take rest, or when we take food, in that case again, the potassium level, or sodium level to the cells, to the atoms, it it polarizes. Okay, and that's why we feel a bit energetic. So that's why there is a need to know about different atomic behavior also. So bioelectric signals are basically generated by the nerve cells and muscle cells. Because we know that there are some atoms inside us. So potassium atom, sodium atom, all this. So single cell measurements like microelectrodes measure action potential, and gross measurements, surface electrodes measure action of many cells in the vicinity. So basically, because of these different atoms inside us, there is always flow of ions. Ionization takes place, depolarization, uh, then polarization, because of the different atoms present in our body. As a result, the electric signals are generated. Bioelectric signals are generated by the nerves and muscle cells. So these can be measured with the help of electrodes. If we put electrodes on the surface of a our body, then as we know that these electrodes are the good conductor of electricity. So if we provide some conducting interface by putting some gel on our skin, so our bioelectric signals which are generated by the nerves cells and muscle cells is can be taken out by putting proper electrodes. Okay. So for example, if we would like to measure the electrical activities of heart, in that case we can put uh, there are different recording systems are recommended. There are standard recording systems, so we can put electrodes on the right area of the chest, so that the bioelectric signals which are generated from say heart with the help of nerves and muscles, so it can be passed through the outer electrodes which will be put on the right part of our chest, and then it can be recorded with the help of some instruments, and then it will be displayed. Okay, so this is about the bioelectric signals. So bioelectric signals are generated by nerve cells and muscle cells. So we can say that electrocardiogram signal can be considered as a bioelectric signals. Then we have a biomagnetic signals like brain, heart, lungs. They also produce extremely weak magnetic fields. And why this happens actually? Why electric signals, magnetic signals, bioimpedance signal, how they are present inside us? That's why we started our discussion with the different levels of organizations, that we have different kinds of atoms. Like we have iron, potassium, sodium inside our body. So because of this different level of organization, it also uh, it also becomes responsible for providing different kind of bioelectric signals, biomagnetic signals. So even so magnetic signals, you see, it's a biomagnetic signals. So now we can we can relate it to some philosophical things also. But as we are more into signal processing domain, so we will say that okay, biomagnetic signals basically like our brain, heart, or lungs, they produces extremely weak magnetic fields, and this contains additional information to that obtained from bioelectric signals. And it can be measured using squids. So there is some techniques to measure this. So actually, our human body, it produces biomagnetic signals also. And you see, like that's why our culture or we were so civilized that in Vastu Shastra, or in philosophy, or in spiritual context also, people will say that we have to sleep in this direction. We should not put our head we should not put our head towards north, okay, because there is a magnetic field of earth which will interfere with the magnetic field of our human body. So because of this different level of organizations, which starts from atom, molecule, cell, tissue, organ system, and then human organism, and because of continuous depolarization and polarization between our atoms. Okay, there is a always there is a generation of biomedical signals in form of bioelectric signals, biomagnetic signals, bioimpedance signals, and so on. And it carries vital information about the health condition of a human body. Okay, so I hope this is clear. These are the theory things, and quite easy. You may be knowing, but systematically I am just moving. Okay, so biomagnetic signals, it gives some additional information which cannot be obtained from only bioelectric signals. Then in the similar fashion, we have a bioimpedance signals also, like tissue impedance. Like if we have a thick tissue,
Yes,
pardon.
sir.
So if we have a thick tissue, or if the tissue structure gets changed, then there will be change in the impedance. So and these all like magnetic field, electric field, or the impedance from the organ. So these all these all carries vital information regarding the health condition of the human being or the patient. So this bioimpedance signal, basically tissue impedance, reveals information about tissue composition, the blood volume and distribution and more. So like if tissue is quite thick and the blood volume is more, then in that case impedance may be very high, and if it is less, then impedance value may be low. And then depending on the physiology, okay, and usually two electrodes to inject current and two to measure voltage drop. So once if we know the current and voltage, then with the help of V by I, del V by del I, we can get the impedance of the different tissues. So these impedances are mainly applied to know, to study the EMG signal, that is electromyogram signals, that is our muscle signals. Okay, whereas in order to study brain waves, mainly they study bioelectric and biomagnetic signals. Then in the same way we have a bioacoustic signals. So many phenomena create acoustic noise. For example, flow of blood through the heart. So when blood passes through the heart, heart's valves gets closed and open. Then we have a blood vessels. There is a flow of air through upper and lower airways of lungs, and sometimes also from the digestive tract, joints and contraction of muscles. Uh, Recording. There are bioacoustic signals are also present in the human body, and these are recorded using some microphones. So we have a bioacoustic signals also, like when we take the breathing. Okay, so these all creates uh, acoustic signals. Okay, then we have it again based on the source. Biomedical signals can be classified as biomechanical signals, like motion and displacement signals, like we have a blood pressure. So this pressure is basically, it's a the blood pressure, say systolic pressure versus diastolic pressure, 80 by 120 or 70 by 120. So these are also termed as a biomechanical signals. Motion, because there is a motion and displacement of signals. Pressure, tension and flow signals, a variety of measurements, not always simple, often invasive measurements are needed for biomechanical signals. Then we have a biochemical signals. Sometimes we measure the chemical also, like suppose in say if there is a composition, if there is a change in composition of some chemicals in the body, or in some part of the organ, in that case we can say whether people is suffering from cancer or not. So these all are basically, these are the parameters to judge or to predict about the human condition. So biomedical signals basically, biochemical signals are basically, it refers to chemical measurements from living tissue or samples analyzed in a laboratory. And these are also known as biomarkers. Okay, biomarkers, because it tells about the health condition of the patient. For example, like ion concentration or partial pressures in the blood. Then so these are so ion concentration, if it is high or low, so people can tell about the health condition, or from which disease he is suffering. Similarly, we have biooptical signals. Okay, so based on the source, biomedical signals can be more specific, which can also be biooptical signals. So blood oxygenation by measuring transmitted and backscattered light from a tissue, like estimation of heart output by dye dilution. Then we have a fiber optic technology also. Actually what happens that if a very pure blood is moving from our heart to different parts of the organ, so in that case oxygen level will be high. Okay, but if the blood is moving towards different towards our heart for the purification. In that case, the oxygen level will be low. And when light falls on these two different kinds of blood, definitely there will be some characteristics change. So that can be captured with the help of fiber optic technology. Now let us see what are the different biomedical application domains we have. So the first is information gathering. First, we should. So one application of biomedical signal processing is to acquire the data, because these data are these bio origin signals in form of, say, electrocardiogram signal, electroencephalogram signal. All these basically contains vital information regarding the health condition. So it's very important to gather the data first, to acquire the data, and then the measurement of phenomenon to understand the system, then diagnosis, and after diagnosis we can detect the malfunction or pathology or abnormalities present. And after diagnosis, if some abnormalities find, we have to monitor that. We after giving medicines, or after having medicines, again there is a need to continuously monitor that, and to obtain continuous or periodic information about the system, that whether the person is getting well, or the condition is deteriorating. So we have different application domains in this biomedical signal processing. Then therapy and control, modify the behavior of system and ensure the result. Continuously there is a evaluation process, and then objective analysis, proof of performance, quality control, and effect of treatment. So all this comes under biomedical application domains. But these biomedical signals, though it has an advantage that with the help of signal processing of biomedical signal, one can continuously monitor and can help, or can provide assistance to the medical expert. But at the same time, there are challenges in biomedical signal processing. So one is accessibility. So okay, India is a very vast country, and we have lots of people of different age. So here we have a very easy accessibility, but still like in the foreign countries, there are lots of challenges one has to face if they want to acquire some data from the person. Many things comes ethical clearance, then there is a less population. But here in India, though we have more accessibility, but for certain rare diseases we have a very less people. So data collection is also a major challenge in biomedical signal processing. So one is accessibility, and then we, as there are certain way, if it is a non-invasive process, for example, if we want to measure body temperature, so we use a thermometer. So thermometer is a non-invasive technique because we are not inserting anything inside the body. But there are certain recording system that requires invasive technique of recording, for like electrocardiogram signal recording. So we put electrodes on the right area of the chest. So there is a, and then it is connected with the electronic instruments till display is there. So there is a chance that people may get shock because of some electric hazard. So that's why there are challenges to provide patient safety. And then some patient may feel very discomfort, and he may not like to go for invasive recording system. So we must develop the techniques of recording which are non-invasive, where there should not be any need to put anything inside the body. So that's why these are the challenges where we need to provide very good safety to the patient. We must give preference to non-invasive techniques of recording the signal. So here the research work comes for the signal processing. So like design of systems which can record these biomedical signals, which are non-invasive, simple, okay, And then always, like, we have a physiological signals, like we have a temperature, like body temperature, body pressure, heart pressure, uh, then heart sounds, lung sounds. So these all are basically physiological signals. These are not electrical signals. That's why we always go for indirect measurements, and in that case we need some transducers. Okay, so we always try to measure indirect measurements. Okay, and then as we have different races based on like and then geographical area is different, people's genes are a bit different, so there is a lot of variance in people besides their age, gender, and other things, genetics. But still there are many other reasons also which leads much variance in the inter individual and intra individual persons. Okay, so these are the challenges or the problems which we face in biomedical signal processing. So this all motivates us uh, to 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 go for the research area which can address these issues. And then interrelationships and interaction among physiological systems. Because suppose if somebody wants to, say if a cardiologist is there, so he will be interested in the only heart sounds and not in the lung sounds, because but still, because of interrelationships and interaction among different physiological systems, definitely if somebody wants only heart sounds, but lung sounds will also appear, and some of the frequency components of heart sounds and lung sounds will overlap. That is known as spectral overlapping. So we cannot use directly filter to segregate heart sounds and lung sounds. So and then if we measure heart sounds, then if there is some movement of hand or body while recording, so there is a continuously there is a interrelationships and interaction among different physiological systems. As a result, it becomes very difficult to record the data exactly, or that's why the subsystem of interest may not be isolated. So we cannot isolate heart from different organs when we are alive. Okay, so that's and each system interferes with the different systems. So that's why it leads to acquisition interference, which is a problem, which is a challenge in biomedical signal processing. And then instrumentation and procedures modify the system or its state, and the instruments may have some impedance value, or it may have some internal noise, internal battery. These can also interfere with the physiological system, and it can change the state. So like we have different kinds of challenges in biomedical signal processing. And then different interferences leads to noise and artifacts also, like interference from other physiological systems, like muscle artifacts in EEG recording. So we know that electroencephalogram signal is very low frequency signal and it's very weak. And and while recording or acquiring brain waves, some muscle movement occurs, then it will affect. So that signal will be not of very good quality for this further signal processing. Then there are we know that this EEG signal, electroencephalogram signals are very low level signals. Our brain waves, they have a very low amplitude signals. So that's why these low level signals require very sensitive amplifiers. They are easily sensitive to interference too. And if small noise also comes, it will get amplified and it will interfere. Okay, so limited possibilities of shielding or other protection, non-linearity and obscurity of the system under study. So and it's very difficult to put always acoustic rooms everywhere, in every hospital, in every study. It becomes difficult. It becomes costlier also. That's why this artifacts and interference is a major challenge in biomedical signal processing. Then we know that basically all biological systems exhibit non-linearities, while most of the methods are based on assumption of linearity. So whatever the system we use, we generally find that its performance is very good when it is operated in the linear range, or they are based on the linearity approximation. But but generally what happens that all the biological system exhibit non-linearities, while most of the method are based on the assumption of linearity. Like then exact structures and true function of many physiological systems are often not known, and still like there are many challenges which biological physiological systems, because exact structures and true function of many physiological systems are often not known. Still like it is said that we know much about our visual system, our eye, but we know very less about our nervous system. Okay, so still like lots of things are still to know. And why this happens, and because it is mainly because of the nature of biomedical signals. So let us talk or give some time to know about different nature of biomedical signals. So one is, so would you like to have a break of 5 minutes, or should I continue? Okay, so let us
Sir,
see.
if you require, you can take a break, sir.
No, it's all right, ma'am, as per your
Uh,
wish.
no issues, sir. Then you can continue, sir.
Okay, okay, let us continue. Yeah, ma'am, yeah.
Participants, if you want break, uh, you could mention now. Okay, sir. You can continue, sir.
Yeah, yeah, yeah. So we saw
Thank
like,
you. Thank you. Thank you, Kausalya ma'am.
yeah, thank you. So like we now we have just discussing about the different problems, or rather challenges faced in this biomedical signal processing, like interference with other subsystems inside the body, or maybe our signals are of very low amplitude and low frequency. So lots of then there is a safety measure when we record certain biomedical signals or bio origin signals from the patient. So lots of challenges are there. So that's why it also motivates us to know about the nature of biomedical signal, that what exactly the nature is and why it is so, and how, and then this study help us to apply suitable signal processing techniques. So we know that the living organism made up of many component system, and each system is made up of several subsystems that carry on many physiological processes. We saw this in the first slide, the different structural level, which starts from atom, followed by molecule, cell, tissues, organ, and different organs combine to form organ system, and different organ system leads to a organism. So most physiological processes are accompanied by or manifest themselves as signals that reflect their nature and activities. And based on these structures and composition, we have different kinds of signals. As we saw, like we have a biomagnetic signals also released from our heart and brain. Then we have a biochemical signals, electrical signals, physical signals. Okay, and these diseases or defects in a biological system cause alteration, its normal physiological process, leading to pathological processes. So it's very important here that if we consider the biomedical signals of a healthy person, and if that healthy person say it gets affected, he become ill, he become ill, then his biological signals will also get changed. For example, if we are a normal, our body temperature is say it's a 37 degrees Celsius, but when we get fever, our it will increase. Okay, the body temperature will increase. Similarly, like say our heartbeat, normal heartbeat for adult is, say it's a 72 beats per minute. So if it goes high, or if it goes very low, then it leads to bronchocardia and trachycardia, which are abnormalities in cardiac sense. So that's why the disease or defects in a biological system cause alteration. It causes variation in the normal physiological process leading to pathological processes. So a pathological process is typically associated with signals that are different in some respects from corresponding normal signals. That's why if a person has some pathology, definitely the biomedical signals will get altered, and these biomedical signal will carry, or it will predict about the different abnormalities present in that body. Okay, that's why it is said that biomedical signals carry vital information regarding the health condition of the patient. That's why these signals can be sensed by qualitative or quantitative manner, and these measurements can be scalar, or it may be a function of time, like function of time. So sometimes you see that generally people see the timing, and then they will note down the heartbeats, heart rhythms. Okay, so then like when we and then multivariant vector also, sometime when ECG is recorded using say 12 lead, or say 9 lead or 3 lead, in that case the signal can be expressed in as a multivariant vector. Okay. Then so we saw certain challenges of biomedical signal processing, and also we saw the challenges are because of the nature of the biomedical signals. And now let us see, so that's why, and then these signals carries vital information regarding the health condition. So now we know that these signals are get altered, it get variated, it get deviated when a person has some pathological processes going on inside. So how to capture that variation? So in order to capture that variation, one is okay subjective, but sometimes human have lots of limitations. Okay, so as these signals in the nature of the signal, in the nature of biomedical, we found that these signals uh, got interfered with many different kinds of signals originated from the subsystems. Then we find that these are very low amplitude and low frequency signals. So human, whether he's a specialist, medical expert, still because of the human limitations, because of our visual, or because of our hearing perception, we may miss some of the frequency components, or we may not be able to correctly detect some of the diseases. So and some person may detect, some person may not detect. So it's very subjective for the doctors, and which requires very high skill and expertise. That's why there is a need to analyze these biomedical signals which contain important information with the help of computers, with the help of modern signal processing tools, and to give a computer aided system in order to detect those things, so that it can assist medical practitioners. Okay, that's why here we are going to talk on different objectives of biomedical signal analysis. So the first objective of biomedical signal analysis or biomedical signal processing is to gather information. So information gathering, measurement of phenomenon to interpret a system, then diagnosis, detection of malfunction, pathology or abnormality, and then monitoring, then therapy and control, evaluation. So these all are the objectives. Now, so how to acquire the signal? Now the question is how to acquire or to record the signal. So there are two techniques actually: invasive technique of invasive and non-invasive. So invasive, basically invasive technique of signal acquisition is mainly when we place So invasive means when we put certain components, certain part of recording system inside the body. So that is called invasive. So placement of transducers or other devices inside the body. So that is invasive. Suppose we want to take blood sample to detect tuberculosis, to detect TB. Yeah, sorry. Okay, that is also good. That is also used. Suppose we want to take the blood sample to know about malaria, whether the person is suffering from malaria or not. So in that case, if we take the blood sample, then it's a invasive because we are putting needle, we are putting injection inside the body, and we are taking out some blood. So that will be invasive. Invasive way of acquiring signal, a biomedical signal. So invasive, that is the placement where we place some of the transducer or other devices inside the body. And non-invasive is a preferable these days, and it minimizes the risk. And here we put only on the surface. For example, if a medical practitioner or a doctor, if he or she uses a stethoscope to for the auscultation process to hear the heart sounds and lung sounds, in that case it will be termed as a non-invasive. If somebody uses thermometer to measure the body temperature of a patient, then that will be termed as a non-invasive because it doesn't need to insert something inside the body. Then and it has advantage that it minimizes the risk. And then signal acquisition can be active or passive also. Like active, then it requires some external uh, stimulus, whereas the passive data acquisition refers where no external stimuli is required. Then so whenever we whether it's a non-invasive, invasive, so whenever we try to acquire the data, uh, the human being interacts with the instrument. That's why one important topic of this biomedical signal processing, where we take subjects, or where or in our country or even in the across the globe also, uh, or in standard books, we always find some discussion on the components of human instrument system, and sometimes it is also termed as man-machine interaction system in biomedical signal analysis. So this is also important. So there was a block diagram also. So components of human instrument system. So we as a human, and the recording system which records the data, which analyzes, and then after processing which displays the data, which gives to the medical practitioner for their assistance. So this all comes under the components of a human instrument system. So there will be subject or a patient, then stimulus or procedure of activity, then followed by transducer, which will convert that physiological signals, say blood pressure, into its corresponding electrical signal. And then once it is converted, then there will be amplifier, filter, which will come under signal conditioning equipment. And then after processing, it will be displayed with the help of oscilloscope, strip, charts, computer monitor, and so on. And these components of human, and then it also refers to recording, data processing, and transmission equipments. Okay. Then control devices, like there should be isolation equipment, patient intervention system. If something happens from the power supply, he must be disconnected from that. Okay, then what should be the properties of these instruments? So as we cannot use any kind of instrument when we deal with the human life. So safety must be a priority. That's why there are certain properties of biomedical instruments. Okay, so whenever we procure a biomedical instruments, or whenever we use a biomedical instrument to record the data from a human being where there is a life, so we desire certain characteristics, we desire some of the specific properties of instrument. So someone may ask that what are the good or what are the properties should be when we use instrument for biomedical signal recording. So in that case, we have to keep many points in our mind. So one is isolation of a subject or patient. So instrument should be in such a way that it should completely isolate, so that that person should be safe and comfortable. Then range of operation. So actually range of operation mainly it refers to the minimum to maximum values of the signal being measured. So that range should be suitable. Then sensitivity, it refers to smallest signal variation which can be measured or detect from by that instrument. Linearity, hysteresis, a lag in measurement due to direction of variation of entity being measured. Good repeatability and consistency of measurement. Then signal to noise ratio. Signal to noise ratio should be high. It must be accurate. Okay, then and we discussed. So these were the different properties which we must have in the biomedical instruments. And then difficulties we already have discussed, but still it is in more detail that certain difficulties which we have, that accessibility of variables to the measurement, variability of the signal source, interrelationship and interaction among physiological subsystems, effect of the instrument or procedure on the system, physiological artifacts and interference, energy limitation, patient safety. So these all are the challenges or the difficulties which we face in biomedical signal processing. And then this is a this slide shows general block diagram of a computer aided diagnosis and therapy system. So with all our previous discussions, now these things become very clearly visible, that mainly suppose if we have a patient here, so if we want to record some signal here. So first let me tell what is computer aided diagnosis system or therapy system. So computer aided means with the help of computer, with the help of application of signal processing and computers, uh, we are able to detect some of the abnormalities present in the organism or human being. And this computer aided diagnosis system has been designed not to replace the doctor but to assist the doctors. And there are many reasons which motivates us to, or which there are many reasons which put pressures to the researcher to develop screening systems or computer aided system, CAD, or some software which can automatically detects some of the diseases. Like in this COVID cases also, like we have been the whole world is almost suffering from the COVID for the last 2-3 years. So we saw that many research took place, and then they have prepared a kit which can directly it will take sample and it will tell whether the person is suffering from COVID-19 or not. So it has eliminated the need of doctor to certain extent just for the testing purpose. Okay, it assisted the doctors. So in the similar way, that's why there is a need for computer aided diagnosis systems. In India, it's a very growing population. In developing countries, people are not getting proper infrastructure and medicines on time. There is a growing population day by day, and then there is a scarcity of proper infrastructure, supply chain management to provide adequate medical facilities, and then there is a scarcity of doctors also, and then many many signal analysis, if they are subjective, then some doctors may tell that okay, he's suffering from this, and some other doctor will not be able to catch that. So as per one of the report submitted by American Cardiac Association, they told that even the cardiologists who are expert also, they also are unable to detect the correct diseases, okay, because it's subjective. Sometimes because of humans mistake, we they are unable to detect certain diseases, whereas if person is healthy, but sometimes they are recommended for the meditation, that okay, you take the medicines. So these things have been also reported. That's why there is a need for the computer aided diagnosis system to develop computer aided system which can assist medical practitioners. Okay, so as per report, it was mentioned there. So here it's a block diagram of a computer aided diagnosis system and therapy. So basically here we have a patient. So there are physiological signals which is in the terms of sounds, pressure, temperature. So this must be converted into its corresponding electrical signal so that it can be processed. So that's why here we use a transducer. So transducer, it, if say if we are interested in sounds, so it must be a microphone. Suppose here we are interested to know the blood pressure, then here must be a pressure sensor should be used. If we are interested in the temperature of a human body, then here we must use a sensor, temperature based sensor, and then isolation is required so that there should not be any interferences. Then amplifiers and filters, because biological signals are very low in their amplitude. So after converting that to its corresponding electrical signal and isolation, still its amplitude remains low. That's why we need to amplify these signals, and we have to use filters if in order to in order to remove some background noises present, if any. Then we need to convert analog signal to its corresponding digital signal, um, followed by filtering to remove some artifacts which we saw that it happens for the biomedical signals. Then we try to detect the events and components, and after that these are analyzed and some features are extracted, and it is fed to a classifier to tell whether the person is uh, diseased or person is normal to the physician, so that it can assist. And the whole block diagram can be broadly classified into three stages. One is signal data acquisition, where we have a transducer, isolation, amplifier, and analog to digital converter. And then we have a signal processing, where detection of event and component takes place, and signal analysis. Processing is different, analysis is different. In processing, main work is to extract the features for the pattern recognition and classification, whether the person is abnormal or normal. Then we have, then the question comes that okay, this is the block diagram of a computer aided diagnosis system. Then why there is a need for this? So we discussed in short, but here more systematically it is mentioned that we need this computer aided diagnostic and therapy systems, because humans, like we humans or even the medical experts, those, they are human being, okay, so humans are highly skilled and fast in analysis of visual pattern and waveforms, but are slow in arithmetic operation with large numbers of values. Humans could be affected by fatigue, boredom, and environmental factors. Like if there are like long queue of the patients, even doctors are there, they are keeping themselves hungry for hours and hours, and they are serving in the night, say they are sleeping 2 hours only. So they may get fatigue, boredom, and some environmental factors also, they may affect on their performance. Whereas this computer are inanimate but mathematically accurate and consistent machines, can be designed to perform repetitive tasks, Analysis by human is usually subjective and qualitative. And like when we analyze the signal, if a human being analyzes, then it's quite subjective. For some person it may be, for some doctor it may be like very serious disease. For some doctors it may be moderate, because it's subjective. Analysis by human is subject, inter observer, and intra observers variation with time. The biological signals are fairly slow, therefore this can be analyzed on line by low end computers. Offline analysis by the stored data. So that's why, like, there are some advantages of these CAD systems. Like, we know that biomedical signals are fairly slow, and therefore it can be analyzed by the computers, because human being may not have time to record the signal for 10 days, but computer can record if a patient is under monitor, or if the signals, or we want to see how the sleep pattern of a human being is there. So for 1 month also we can record the data with the help of computers. Continuous data can be recorded, and then it can be stored, and it can be done analysis. And so these were mainly, that's why it tells about the importance of designing a CAD systems. And so as we are discussing biomedical signal processing, so broadly, like, uh, we find that most of the signals which we do find the analysis in signal processing, and we find machine learning, or deep neural networks. So these are mostly applied to most of the common biomedical signals, like ECG, electrocardiogram signal, electromyogram signal, which is the study of the electrical activity present because of the movement of muscles. Okay, electrocardiogram, basically it's the recording of electrical activity of heart. That is electrocardiogram, ECG. Electromyogram, it's a recording of electrical activity of muscle signals, which is caused because of the movement, contraction and expansion of muscles. Similarly, we have EEG, electroencephalogram signal, which is the recording of brain activities of an organism. And then we have a non-bioelectric origin signals also, where there is no electric signals there, like blood pressure, heart sound, speech signals. So biomedical signals can be broadly classified into two categories also. That is bioelectric origin, where we have electrocardiogram, electromyogram, electroencephalogram, that is brain waves. And in non-bioelectric origin biomedical signals, we have blood pressure, heart sounds, lung sounds, respiratory sounds, speech signals. So these all are non-bioelectric origin biomedical signals. So here, like, we have lots of signals: electrocardiogram, electromyogram, electroencephalogram, blood pressure, heart sound, speech signals. So seeing the time limit, I have just discussed here only electroencephalogram signal. Okay, so here brain waves, electroencephalogram signal. So whenever brain waves comes, we always go for, it directs us to CNS, that is central nervous system. So there are two components mainly: the brain, and then followed by the spinal cord. Okay, so brain and spinal cord are the two main components of a central nervous system. And this brain is bathed, it is bathed in, there is a liquid bathed with cerebrospinal fluid. And the nervous system, there are certain divisions, like anatomically, like nervous systems uh, have a like brain, spinal cord, and then there are peripheral nervous systems, PNS, connecting central nervous system to body organs and sensory systems. Then there is a directionality of nerve connectivity. So there are two types of nerves. One is sensory nerves, and another is motor nerves. So sensory nerves, basically it transmit the signal to the central nervous system, whereas motor nerves, it transmit signals from the central nervous system. Okay, so that's why these sensory nerves are also known as efferent, and motor nerves are known as efferent. So actually, from central nervous system, there will be a signal transmitting towards the body to further reaction. So that is known as motor nerves. So it transmit the signals from the central nervous system. And if we get a pin, or we if or when when some signals goes to CNS, that is central nervous system, then it is because of the sensory nerves. Okay, by seeing something, it automatically goes to brain. So this is where our sensory nerves has worked. Then functionality. So nervous system is also categorized based on the functionality, like somatic nervous system. So basically it control muscular activity and relay physical sensation. Then there is a autonomic nervous system, which regulates bodily activities beyond conscious control, like cardiac activity, muscular activity of internal organs. So these are like it's beyond our control. Okay, so even if we're sleeping, even we want or don't want, the cardiac activity will go on. Muscular activity of internal organ will always be there till we keep ourselves alive. Then there are sympathetic sympathetic and parasympathetic system. Okay, so sympathetic, it dominates during physical activity, and when we get ourselves relaxed, in that case parasympathetic nerves comes in action. So these are the some of the different uh, projections, or different views of our brain. Okay, so we are not going in detail here. This is also like we have a frontal lobe. Okay, frontal means the frontal part where we have this forehead. Okay, and then in our like in back, it is like occupational lobes. Okay, then we have a central lobe. Okay, we have different parts, and these all are related for different, for controlling different organs of a human body. So that's why here it is divided into different part, and each have different function. Some will be connected to visual part. So if something gets damaged in one part, it may affect our organ. Say it may affect our eye. So these are the different parts, and then here like one part of the brain is showing here, and then these different parts, it controls the this part in our brain. It controls different. Like here, it will control the foot, leg, thigh, pelvis, trunk, neck. Okay, hand, upper face, lips. So these all are controlled by certain part of the brain. So if something happens here, it may directly affect our different organ movements, or balance. Okay. So major components of the brain, if we see, so major components of the brain contain cerebrum. We have a 5 paired lobes: frontal, parietal, temporal, occipital, which is backside, and insula. And these all are, this cerebrum is concerned with the higher brain function, storage of memory, perception of sensory impulses throughout process, and so on. Then we have a another major component of the brain is thalamus. It relays center. It is a relay center. It is a relay center for all the sensory impulses. Then we have a hypothalamus. It's a automatic nerve center. Then we have a cerebellum. One was cerebrum, okay, which is responsible for higher brain function, like perception, storage of memory, and so on. Likewise, we have a cerebellum. Actually, it is responsible for coordination of skeletal muscles contractions. And then we have a medulla oblongata. It is the centers for reflexes involving in sneezing, coughing, swelling, and so on. And this is so it is showing that a crossed exterior reflex causes a reciprocal inhibition of muscles within the opposite. So actually it says that how things get balanced because of the brain. And this shows about the recording system, that how to record electroencephalogram signal with from our skull. Okay, so here like we will put in this area we will put different electrodes here at specific distances, and we can get the electrical activity of our brain. Okay, so there is EEG recording system. So mostly this 10 by 20 EEG system is used for recording brain activities or for recording uh, electroencephalogram signals. And this basically this 10/20 EEG system, it refers to the fact that actual distances between adjacent electrodes are either 10% or 20% of the total front, back, or right left distance of the skull. This 10 to 20 system is also termed as international 10 to 20 system, and it is well accepted internationally, and it's a method to describe and apply the location of scalp electrodes. We put electrodes on our scalp in context to EEG examination, polysmograph, sleep study, or volunteer lab research. We record for the various reasons, maybe to study the sleep disorder of a patient. And this system is based on the relationship between location of an electrode and the underlying area of brain, specifically the cerebral cortex. During sleep and wake cycles, the brain produces different objectives, different patterns, which are quite distinguishable, which can be detected by electrodes on the skin. These patterns might vary and can be affected by multiple extrinsic factors like age, prescription of drugs, somatic diagnosis, or some medical history. HX here, this HX term is termed as medical history of neurologic insults or injury or trauma or substance abuse. Okay, and this why we do this recording of electrocardiogram signals. So as we previously discussed, that these biomedical signals, whether it's a electrocardiogram signal or in this case it's a electroencephalogram signal, EEG, it contains vital information regarding the health condition. So this EEG, electroencephalogram, that is the recording of brain activities. It contains vital information regarding the mental state of a patient. So the recording and analysis of this electroencephalogram signal can help us to know about various applications of EEG, like in order to know about sleep disorders, or even um, to interface this brain with some computer, so brain computer interface, or epilepsy, a kind of a disease. So this is the recording system, how recording technique, it tells about, this slide is mainly kept to know the recording technique, that in the 10 to 20 EEG recording system we put bipolar electrodes, because once when we put bipolar, then only we can measure the voltage differences, and one unipolar, it is for the reference. Then inter-electrode distance we keep as 4.5 centimeter away, so that there should not be interference. Then we keep sampling frequency of 100 hertz, because we know that these brain waves are of very low frequency signal, should be increased to 64 or higher for brain mapping application. So like sampling frequency should be increased to 64. Then we know that electrocardiogram signal is basically, it's the electrical activity going inside the brain or on the scalp. So So these are the some of the properties of electrocardiogram signal. And when we measure, so this slide is very interesting, and you please you can see the different types of waves recorded from the brain waves. So when these 10 to 12 electrodes are put on the skull, and when this electrical activity of brain is recorded, we find that there are different kinds of different components of a brain wave. And this figure 59.1 in this slide, it reveals different types of normal electroencephalographic waves. So these all are normal. So here what we find, there are four components here: alpha, beta, theta, and delta. So here we find that delta has a very low frequency, whereas this beta and alpha are having more frequency here. Theta is intermediate. And we, if we see the voltage level, so the voltage level of this components are very low. We see that the average amplitude is just 50 microvolt, which is very, very low. That's why we need a big, very good amplifier. So this was for a normal human being, it has been recorded. So different types of normal electroencephalographic waves. And now this is shown for progressive change in the characteristics of the brain waves during different stages of wakefulness and sleep. So when person is very alert, or if he is sleeping, so in that case different kinds of waves have the dominance. Okay, so when a person is normal, here we have a four waves: alpha, beta, theta, delta. And then if a person goes from different stages, so there is a change in the signal components. For example, if a person is alert, is a very alert or wakeful, then in that case this beta wave will have more dominance here, beta waves. And if he's quite wakefulness, he's quite not very alert, then this kind of wave will come. And then at stage 1 it will show low voltage and spindle here. It will, so then stage 2 and 3, where theta wave will be more dominant. And say earlier he was very alert, he was very active, then he came down, he become a bit lesser wakeful, then after some time he went to sleep, and then slow wave sleep. So it is the recording when a person was alert, then he became less alert, and then he goes for a sleep. Okay, so in that case when he was very alert, then beta wave was dominant. And then when he was quite awake, then many frequency component disappeared, and only one this sample came. And then that amplitude also goes down here. And when at stage 2 3 we have this kind of wave recording, which has a magnitude of almost 50 microvolt. And then slow wave sleep, then delta waves appears more. And when he completely sleeps, then beta waves come into picture. Okay, so this is shows the recording for progressive change in the characteristics of a brain wave during different stages of wakefulness and sleep. So when he was very alert, in that case the wave was like this. Okay, so if a person is never he become if a person is not able to make himself alert, then in that case this may be missing for that person. And if it is doesn't coming, then doctor may say that he should go for some meditation, or he should focus, so that this can be means therapy can be done. Okay, then clinically useful as distinct brain state shows different characteristics. So like if a person is very excited, so if he's watching some very exciting cricket match on television, then his brain waves will be like this if he's very excited. And if he's a very relaxed, suppose in case of some meditation, or if he's very happy and relaxed, in that case the brain waves will be like this. Then in case of drowsy, it will be like this when he falls asleep. And then in deep sleep, it will be like this. And when person goes in coma, the brain wave will be like this. So clinical importance is manifested in this kind of a signal. So this recording can help people to understand the mental health condition of a human being. Then this is in different types of epilepsy. So if he has a grand mal epilepsy, then voltage level is very high, frequency is very high. Okay. And then this is the normal activity of a brain where the amplitude is not very high. But seizure activity means if a person is mentally imbalanced, is suffering from some mental problem, in that case the brain recording is like this. So if we have this kind of a recording, definitely we can predict about the human being that is suffering from some mental problem. So with this, I would like to thank you for this session. And if time allows, I have kept one more session for you. This is actually now this I wanted to take, but just a minute. Yeah, this one. Can you see this one, this slide? Phonocardiogram signal analysis for diagnostic
Yes, sir.
purpose. Okay. Okay, so like it's almost going to be 12. So what I can do in the next session, just within 10 minutes, I will finish this. I will finish this within 10 minutes in the next session, and then we will go for MATLAB things. Okay. Uh, so I think I will stop here, and then if you have some queries or some questions, we can discuss. But just to rewind the things, just let me give the highlights that basically we started with the term biomedical signal processing, and then we saw biomedical signals are those signals which are originated from physiological processes, or which are originated from some organ. And then we saw that these biomedical signals must be classified first, because there is no single algorithm exist in the signal processing which can be applied to all the classes. So based on the nature of the signal or based on the origin, biomedical signals have a classification. Then we found why we go for biosignal processing, what are its advantages, what are the limitations or the challenges, and what are its applications. Okay. And then we saw electroencephalogram signal in detail. And and we also saw man machine human interaction system in context to biomedical signal processing. So like at least we could able to know about different aspects of biomedical signal processing. In the next session we will be more focused toward demonstration on signal processing, that how to filter the signal, or how to use or how to extract feature, and how to classify whether it's a normal or abnormal.